Thank you. I'd first like to thank the organizers for inviting me and letting me speak in this very important event of the birthday of Guy Henniart, my good friend. And I'm really pleased to be here for that. Guy and I have been knowing each other for a long time, and we never officially collaborated, but we have non-officially collaborated quite a bit. We have both been very interested on each other's work. At the moment, Guy is collaborating with my former student, Louis Lomelli, on doing the p-adic, the characteristic positive of the theory. And he and Bushnell wrote the appendix to our paper in the Annals. And that may be a collaboration. That was very helpful to us. And that's the paper when symmetric cube was done. And I wish you many, many years of great health and great mathematics as I expect it. All right, this is something that Guy has been interested and he has done some work on it. So it's the issue of the equality of root numbers for symmetric and exterior square L functions. This is basically, the group is GLN. There is the local Langlands correspondence that attaches to every representation of the, so let's take F p-adic. Attaches to every representations of the Freydoon group, in fact, to GLNC, so n-dimensional representation. A representation pi of rho, so this is continuous n-dimensional and Frobenius semi-simple. Pi of rho, irreducible, admissible representation of GLN of F, satisfying a number of conditions. This is pretty well known internationally and around this point. A lot of people have worked this problem. Finally, this was done by Harris and Taylor and Henniart as well. And the main condition is that if you look at the gamma functions, suppose I take two representations. Let me write this. I could just write it like pi going to rho. So if I have two representations, pi 1 and pi 2, coming from, let me start, rho 1 and rho 2. In fact, they don't have to be to the same, they don't have to be of the same dimension. And attached to it, we take pi of rho 1 and pi of rho 2. Then chief among the properties is that if you take the gamma function of rho 1 tensor rho 2, we always fix additive character psi f, f check, and you want it to be non-trivial. This object is supposed to be equal to gamma of s pi of rho 1 pi of rho 2 psi f, and this is the Rankin-Selberg factor. Now, of course, these gammas are just the ratios of, I'll just write it, epsilon of s, L of 1 minus s, and tildes. This, okay. Divided by L of s. And the same thing for those. So, and this equality and Langlands classification basically will show you the equality for root numbers and L functions. So this equality is fundamental in doing anything. And this will be what we will be using. Now, the result that I want to discuss is to look at the case when we compose this row further on by either wedge squared or sim squared. So this goes to GLN and minus plus 1 over 2 of C, the symmetric square and exterior square representations. And then you look at this composite map. Let me just take one of them. And then there are factors of Artin that you can define for this composite map. And then there are factors for wedge squared, which I defined in some generality in my work. And then similarly for the symmetric square. And the question is that these Langlands correspondence must be quite robust, so these guys should be equal. And of course, there is a very quick identity. In fact, I'm going to take and this is very quickly can be seen to be equal to and similarly for the other one. And this is so pi is pi of rho, and in this side you're gonna have the pi wedge squared psi f and gamma of s pi sim squared psi f. And it is clear that if you know the equality of these two, you're going to get the equality of these two. So it's enough to prove only for one of them. Now, what I'm going to discuss today, this is something that Henniart had looked at in his 2010 IMRN paper. He looked at and he proved it for the L functions, even for the twisted L functions. But for the gamma functions, or say root numbers, he proved them all up to a root of unity. And that root of unity is important. And in that paper, he said it very clearly that you would need a stability to do it for the equality of gamma factors in general, for these cases. Now, what I'm going to do today, we are not still done. It's taking sometimes, but we are stuck in the analysis, but we are pretty close, we feel. This is a joint work with Cogdell and my former student Tsai, and we think, Jim and I think we are pretty close in getting it. I will explain the analysis involved in the case of GL2, because that was something we couldn't even do that two months ago. So, but it seems that we can generalize that. But there are two parts to this. One part is very robust. It has nothing to do with these things. It will reduce the equality of these factors to something which we call stability for supercuspidals. And that I can go through. There is a lemma in there which Henniart proved for us, so that's another reason to do this in his birthday. So let me start reducing the problem of equality to what I call the stability of, in the supercuspidal. Well, let me start. First of all, this works for any system of, this idea should go through for many cases, but we use it in this case. So let me start with this proposition. So the first thing is that we want to prove is, this is theorem, and we want to prove that psi f is equal to, let's put it for gamma. It's the gamma of s pi of rho h2 psi f. Now we'll start with the proposition, which I'm going to call it proposition 2, and reduce it to a problem in p-adic analysis. Now, this is that suppose n is some integer, some natural number, some positive integer, and let's assume rho is n-dimensional, irreducible representation of the V group, WF. Then for all highly ramified characters, chi of F star, we have the equality, but under twist by this highly ramified character. We have that F H2, I'm going to write it in the form rho tensor chi is equal to gamma of S pi of rho tensor chi H2 psi F. So this I'll call stable equality. And this I will prove in the irreducible case. So then pi of rho is supercuspidal. And if you can prove this together with what we call the supercuspidal stability, you're basically going to get the equality. So let me tell you how one will start proving this. The proof would be an induction on N. Induction on N. All right, so let me start with the lemma that's the one that Henniart showed us how to do it. I asked him and he told us, gave us a proof. This goes as follow. Fix N in N and the character omega naught of F star. Okay? Then there exists K, a number field, rho, a representation, rho tilde, n-dimensional, irreducible representation of the V group of this global field, such that if I write rho W tilde to be equal to rho tilde restricted to the V group of KW, W place of F, then the following holds. Then the following holds. Let me write the results over there. First of all, there exists a place V such that Fv is equal, Kv is equal to F, our local field. Now, then of course, we know we have this thing. Let's just concentrate at the prime V, then rho V tilde, this prime V that we want it to be irreducible. And then we want determinant of this to be equal to that omega naught. Of K, sorry. Okay, so we want the first condition be that at some prime V, Kv is equal to F, rho V tilde is irreducible, and determinant of rho V tilde is equal. Every other finite prime for all W finite, W different from V, rho W tilde is reducible. And then 3, we want that this pi, pardon me? I already said not for them, for that one particular. Yeah, no, nothing about the determinant. Finally, we want that, let me define to be tensor product of all the local. So these are the Harris-Taylor-Henniart lifts. I mean, no, not lifts, but correspondence. And let's define this to be that thing. This is cuspidal, is a cuspidal. Well, that's okay. I think we can do cuspidal. Cuspidal automorphic representation of GL and of AK. So, oh, this is W. I have reserved V for that one particular place. So I'm using W for everywhere else. So this is, now, using this lemma, we're going to start proving this proposition. So for the lemma, we're gonna use this lemma, and so we want to start with the proving proposition 2. But before I do that, let me state the analytic result that we need. Proposition 4. If I take these two factors, suppose this is stability for supercuspidals, and this is the usual stability statement, pi 1, pi 2, supercuspidal irreducible representations of GLN of F, such that they share a central character, omega pi 1 equal to omega pi 2. Then for all highly ramified characters, how high it's ramified, it depends on pi 1 and pi 2. Highly ramified characters chi of F star, the gamma factors are equal. Gamma of S pi 1 tensor chi wedge 2 psi F is equal to gamma of S chi wedge 2 psi F. Now this is the thing which has to be done using analysis, and this is the part we are working on. With, maybe I should use, that's the main goal. Assuming proposition 4, which is a completely different game, it's a 2 different approach. Using this, we're going to prove the lemma 3. I'm not going to give the proof. I mean, but it's going to lead to a proof of proposition 2. And then when you have that, you can then prove the equality using a local global argument. Yes. Okay. Yes, right. Yeah. And that's hard. Now, let me, with these tools, I want to start proving, first of all, proposition 2. So using lemma 3 and proposition 4, we want to now prove proposition 2. Proof of proposition 2. While lemma 3, we're going to have a K, a rho tilde, a KV equal to F, rho V tilde, which is rho tilde, restricted to F. And and we know that rho V tilde is irreducible, and rho W tilde is not irreducible for any W different from V. And we know that determinant of rho v tilde, I'm going to call this is equal to omega naught, which is omega naught is what we fixed, and omega naught is really determinant of our rho. We had a rho originally, so I compute determinant of that, and that's omega naught, and I would want this thing to be equal to omega naught. Now, then, of course, we're going to have this pi of rho tilde, the tensor product of these representations, and this is cuspidal automorphic. Then we write the functional equation for so, and I take a Grossen character. It's a Grossen character. Grossen character of K. And then we write we know that by the induction hypothesis, proposition 2 is true for all these things when W is different from V. Because the sizes are smaller, you have smaller supercuspidals that you're dealing with. We have the equality. We have stable equality. I'll just write it for the bookkeeping. Gamma of S, VH2 of rho tilde W, tensor chi tilde W, and psi W is equal to gamma of S pi of rho H2 and psi W. Of course, we have a global psi. Let me use this, now that I'm using it for everything else. And we want that thing to be equal to psi f at the prime v. So at all other finite places, so W is finite. And W is different from V. By the induction hypothesis, we have this equality for all of them. At Archimedean primes, now V, W equal to infinity, we know the equality without even the twist. Equality is known. So this is in my 85 Duke paper. Now we compare the two functional equations, one for the Artin L functions and one for these other L functions which came from the other method. We compare these two things and we're gonna have the equality at V. So we're gonna have gamma of S, H2 of rho V tilde tensor chi V tilde psi. Now it's going to be psi f because we are in that place. And then the other side, gamma of S pi of tensor H2 and psi f. So we have the equality at that prime. Now comparing functional equations. We get this equality. So this will prove the proposition. Now we'll put this, not the proposition, but this will prove this equality at the prime V. But let me. Or we prove the equality of the factors for real places, at Archimedean places. Didn't I say that? Yes. Yeah. Oh, I should have said that. Okay, sorry. Yeah. Yeah. Yes. Yeah. Yeah. Of course, you can't have it at all the places. At all the bad places that you can control. At all the ramified places, when there is some problem, you will assume it to be ramified there. All on ramified places, they are equal. Now, so what have we shown? Let me get a conclusion of what we have proved. We have proved there exists one representation So we have shown that there exists, let me call this, we have shown there exists a pair. Let me put definition, this thing, rho with tilde. Let me define then pi naught, pi of rho with tilde. We have shown, conclusion of this is that there exists a pair, pi naught, such that proposition 2 is valid for them. Okay, so this just simply, we have the equality of x, the rho naught of h2, rho naught tensor, some highly ramified character chi, and then psi f is equal to gamma of s, pi of rho naught, pi naught tensor chi h2 psi f. We have shown this, but only at one particular representation. Now we look at the diagram. So I have here rho naught going to pi naught. I know that the gammas are equal. Gamma of pi naught. Of course, these are highly ramified. Let me put the chi's in there. Put the chi's in there. Now, there is a, I mean, if you look at Artin factors are stable. This is, I mean, goes back to Deligne and Deligne-Henniart. We know that gamma of any rho tensor chi, these two are equal to each other. This is by Deligne, Henniart. I think Deligne also has some by himself. So we know these two factors are equal to each other. Now, proposition 4 will tell us that gamma of S, let me just forget about S and psi, pi tensor chi is the same as gamma of pi naught tensor chi. So then you get this equality. So this proves proposition 2. Proposition 2. So this is how you will get the proposition 2, but of course it relies on this one, on proposition 4. Now let's try to, so far we only have the stability, I mean we have only equality up to stability. That's the, well, let me. Now, as soon as you have the equality, I mean one thing that is very crucial is that if you know stability for supercuspidals, you cannot prove stability for arbitrary. Because there is one important tool in all of this, and that's multiplicativity. That if you have induced representations, then the gamma factor is product of gamma factors of the inducing data and so on. But the trouble is that if you have pi 1 and pi 2, they are arbitrary supercuspidals. I mean, pi 1 and pi 2, and they are arbitrary, irreducible, admissible. they embed into very different parabolics, induced from very different parabolics, supercuspidals. And when you write the multiplicativity, these factors, they have nothing to do with each other. They would be even in different degree. And for that reason, it is clear that even if you have proposition 4, you are not going to be able to prove the stability for arbitrary, irreducible, admissible representation. So you cannot just produce the idea of, okay, we have this thing, then we can use a local global argument and get it. It's not possible. On the other hand, at the end, when we prove everything, we will get that. We will get the stability out of this because these things will be the lean factors, will be Artin factors, and they are stable. Now, let me finish off having proposition 2 proved. Let me now prove theorem 1. So one thing is that when you have on the other hand, if you have the stable equality, you can extend it from supercuspidal to arbitrary, because then you can use multiplicativity. Now, corollary 5, the stable equality holds for arbitrary rho and pi of rho. So it doesn't matter if it is irreducible or supercuspidal because of use multiplicativity. Pardon me? Yes, right. Yeah. We need this. Yeah. Use multiplicativity, which basically says that if you have a representation induced from a data, then the gamma factors will be product of gamma factors coming from those things. They are not just going to be exterior square. They may be ranking products. They may even be symmetric squares or things like that show up. But eventually, everything reduces to that case. Use multiplicativity to conclude. And induction for induction from supercuspidals, and then apply proposition 2. Now we can implement the ideas that Henniart and Harris and Henniart had, and get the equality will be done. So all right. Now, now, proof of theorem 1. We just do the idea. This is 1998 paper of Harris in Invenzione, and Henniart used it. I have your paper 2009, right? Okay. So follow Harris 1998 Invenzione, and Henniart 2009 IMRN. Just, now it is not very hard to guess. You just prove it for the basis of the Grothendieck group of finite dimensional representation of the Weil group. So what you do, you take rho to be, we assume rho is monomial. then you can produce a global object that carries this. So then there exists a number field K, and the representation of WK. And again, you define a pi tilde by tensoring these pi of rho W tilde. And let me call that pi tilde. So then you have this rho tilde to pi tilde. And this is the automorphic representation of GLN of AK. And then this you can do. In general, this is not possible. But in this case, and then use the functional equations. Use functional equation for the two L functions, L of S rho 2, beige 2, rho tilde, tensor. Well, I'm going to come back. I'm going to have to use also, because I have to use ramification. Just these same settings. Rho. And then some global character, psi k. Of course, not doesn't sit for this is global, so it goes away. And then you have L of S, pi of, or pi tilde, tensor chi tilde, and beige square. Compare the functional equations for these two things. We will assume that this thing is highly ramified, chi W tilde, highly ramified at all ramified W, and W different from a place V. I'm going to, as usual, just embed my representation pi of my rho tilde will be my rho, and my pi of rho tilde would be my pi. And then you just compare these things at all the places, and you assume this is highly ramified for those finite primes which are W finite, which are different from the ramified ones, and you have the equality of gamma factors by proposition 2. By proposition 2, position 2, and that Duke paper, 85, and I will assume that chi V is equal to, this is V. I will assume chi V is just 1. And then by these two things, you will get the factors. Using the functional equation, you will get the equality of the factors. So of course, instead of proposition 2, you have to apply really this corollary 5. Because now the components don't have to be supercuspidal. They could be any. Okay, so this will prove the theorem in this case. Now, so it's clear that the hold-up is in that's analytic. Hold-up is in that analytic. So let me now tell you what we know about that. All right. Our original idea was that I will explain, first of all, how these gamma factors on the other side, on the automorphic side, are defined. And then using that definition, we tried to use an expression, which I proved in a 2002 IMRN paper, try to use that expression to prove the stability, to prove proposition 4. I'm not going to prove it, but I'm going to give you indications of the proof. Yeah, I want to prove it, yeah. Okay. Now, Oops. All right. To define these factors in the representation theoretic side, you have to use a triple, a reductive group, a Levy subgroup, and a representation on the Levy. And to get this particular wedge squared factor, you have choices. You can take it to be SO2n, or you can take it to be equal to SP2n, or they're similitude groups. Now, choice of SO2n is the simplest because there is only one factor which appears, one gamma factor. So basically, these are, when I mean gamma factor, I mean if you look at globally at the Eisenstein series attached to a data, global data like this, then you have the constant terms, and the factors that appear there in this case is going to be L of S pi VH2, 2S of course, and times L of S pi and standard. Now this is the case of SP2n. The case of SO2n, you don't get this. But the trouble with SO2n is that when n is odd, the center is this Levy. The Levy is Ziegel Levy. M is GLN in all of these for both of them. And the problem is that when n is odd, this thing is not a self-associated Levy there. So the machinery of that paper in 2010 2002 doesn't apply. We are using my IMRN paper. So this we could not use. This we could use, but then there is also the fact that the center of this is not connected, so we extended it to GSP2n. So the group that we work with is GSP2n. Now then, GLN is the Levy inside this. Of course, Levy here is M is GLN cross GL1, but that GL1 is really in the center of the big group, so you don't have to worry about it. So that's you can just put 1 on this, you put then pi, let me call it pi naught, and pi naught is just pi. I'll take it to be pi tensor chi. So then the point is that there is, the functional equation comes in from using the so-called local coefficients. Local coefficients. And what is proved, so let me denote it by C sub psi f of S and pi, and it turns out to be the gamma functions S pi standard times gamma of 2S pi wedge squared. Of course, I'm missing the psi, but don't worry about it. And the formula gives an integral expression, integral representation of the inverse of this. So this is proved. So there is a Mellin transform of what we call of a partial Bessel function. That's the problem. The problem is that what shows up in the formula is a partial Bessel function. It's not a full Bessel. A full Bessel function is an orbital integral, a full orbital integral. But the theorem that we proved dictates on us a particular type of, but it's not a full integration, it's an integration over some compact set. Otherwise, you won't have any convergence. And so then this is, of course, going to be equal to these gammas. Now, if we show this expression, this Mellin transform is going to be an integration over the open cell, over the big cell of GLNF. So that's C of WL. That's a big open set inside GLNF. And the Mellin transform is really an integration of this particular function over there. So that's the... Now, so let me write down a little bit of a formula which tells us what this partial Bessel function is. This partial Bessel function, I'm going to write it. First of all, we're going to be dealing with matrix coefficients. So F will be a matrix coefficient of the representation pi, and this will be CC infinity of GLN. So G is now GLNF. And with the fixed, which change according to the fixed central character, omega pi. So compact support mod center, transforming according to omega pi. These are the type of functions that we'll be looking at, and the partial Bessel function. So there is a, let me first write, and then I'll try to explain. So U is always the unipotent inside GLNF. And this is an integration over, so I'll take this function, F, X, G, U. These are the variables of integration. They are U cross U divided by stabilizer of, I'm going to try the stabilizer in U cross U of G. This is just very crude, I'm just for the point of. And then there is a function phi. This function is a function of compact support in N, unipotent radical of this levy, the Siegel levy. So you may look at it as something on the compact support on the Lie algebra, and this is going to be integrated over, and then of course we have the character. I have an additive character, I compose it with the standard splitting, so I get an additive character of U. So XU dx du. I'm sorry, let me, you're right. Let me call it H. Yeah, that's better. And that would be H. Yeah, this will be, but this is GLNF. Yeah. Did I? The big group is G, because I told you like that. I should not have. The small group is GLN, which is H. I changed it to H. So did I do that? No, this is G. This is H. Okay, sorry. I should have used a different. What? I'm going to explain. I mean, I was stopped when I finished this sentence. So U tilde is just the standard thing. U tilde is going to be equal to. Now, N is really, if you look at Lie of N, it is N by N, but it's second diagonal symmetric. That's what the N is. And then U tilde is just WL, U transpose WL. Okay? And WL is the long element in GLN. Long element for GLN. Okay, so this is the partial Bessel function. If this thing wasn't there, this would be truly a full Bessel function, and we know a lot about this. We understand this much better than this. Now, unfortunately, we have to deal with this. Phi is a function of compact support. I'm going to put it in a compact support on N, unipotent radical. So if you want to look at it, it will be really, you can identify N by its Lie, and the Lie is like second diagonal symmetric matrices, and you may be looking at the function there. So inside, if you want to put it inside, I'm just being very sketchy. Inside Mn, but will be of particular type, an exhausting sequence of particular type. Is this? G is now, G is N. I mean, the G is GSP, 2N, and N is the unipotent radical of Siegel, parabolic. Then I yeah, the small g is in, of course, the small g is in H. is in GLN. Anyway. Oh. All right. Now if that phi wasn't there, that would be a Bessel function in this, in the sense of Jacquet and Ye, for example, or in general sense of different people. And there is a germ expansion for that. But we cannot use that germ expansion because that's for the full Bessel function. So the main hope was to, first of all, we thought that if we have a supercuspidal, this phi will go away if f is, depending on f, phi will go away, and that's not true. There are some supercuspidals you can do that, but most supercuspidals you can't do that. You cannot find a matrix coefficient when things will be supported in the big cell. Because you are integrating over the big cell. If you want to prove stability, you need to have uniform, you need to have some uniform smoothness. To prove any kind of stability, one needs a uniform smoothness. Smoothness for this B sub phi. Let me just put the variable there. And we couldn't, you can't, because, yeah, and you want it to be uniformly smooth on the big cell. That basically means that you want this thing to be supported, whatever is inside some function to be supported compactly inside the big cell. And you for an arbitrary f, you can't do that. Now, let me explain what we can do. So we cannot use the germ expansions of Jacquet and Ye for these partial Bessel functions, but just because of the existence of that phi there, but we can try to get close to it. Now, let me explain how we do that. Let me take n arbitrary first. What I'm going to do, we're going to start erasing off from the smallest set. We try to write this B sub phi in a form that we can get rid of the things step by step, just erasing off first a small set, taking the difference, erasing it off in the next one, and going on. And in each step beyond the first step, you will have some kind of smooth compact, some kind of uniform compactness in some direction. That's the hope. And then use that, because when you are proving stability, you need some kind of uniform smoothness, and if you have a compact thing, you will get a uniform smoothness. Now, first of all, let me take now two representations. I'm going to use supercuspidal, reducible representations of H. H is now GLNF. And central characters omega pi prime. You can write it equal to omega if you want. Let me take matrix coefficients. Matrix coefficients of pi and pi prime. Let me assume that let me define W H of G to be the Whittaker function. So it's going to be f of UG psi inverse of U du, and that's integration over U. And then we would want that both of these things are equal to 1 at identity. So they do not vanish at the big cell. So and then we, let me take Z, center of H, which is just GL and F. H is I'm identifying the F points. The integral is over U. H is here, sorry. H is here, right. And then I have the center of H, which is GL and F. I'm going to look at W, an element in the while group. Then I'm going to look at omega sub W. Now, this is the union over all the elements which are dominant over W of C of W prime. Now, this is the broad double coset for that particular element. And this is broad over there. So this means that C of W is contained in C of W prime bar. Okay, this is open. The smallest one is closed inside here. And then we look at and C of W prime is just Borel of GLN, W prime, Borel of GLN. Borel of GLN. And so these are and so we have this thing in here. Now, one thing that you want to notice that omega E is just all of the group, is all of the H. Omega is H. And let me look at the situation when omega, let me define omega naught of E to be equal to G, remove from it the small cell, the trivial cell, the cell attached to. And let me compute the B sub phi. Let me compute B sub phi at the center for H and B sub phi at the center for H prime. If you compute these two things, you will see they are both equal, and they're going to be equal to omega of Z, and then phi of Z. Z will appear there. I mean, when you do the broad decomposition, Z will appear in N, so you can really look at it like that. So if I take the B in the difference, that's going to be 0. So now the question is that if I take this equal to F, now I have a function. It's in CC infinity of H and omega F. I have a function, but this thing vanishes on it. I want to see if I can somehow, bottom Z is the center. Yeah. I want to see if I can somehow replace F with a function which is of compact support inside this difference. Okay, and these are the kind of lemmas that Jacquet and Ye proved. I mean, Jacquet has an appendix to whatever version of our paper. These are a very nice set of things, but they are really not so easy to be generalized, but we have generalized many of them already. How much time? 5 now. So one lemma that we can, I mean, there's many lemmas we have proved, but the one which is, so this will be a lemma, it's in a special case of a general lemma we proved. Of Jacquet and Ye, we have extended. This is just like this. Suppose B phi of Z and F is equal to 0. Z is the center for everything in the center. F is in CC infinity of H and omega pi. Suppose you have this thing. Then there exists the function F naught. Now this function F naught is going to be in CC infinity of omega pi. I called it, let's call it CC infinity of omega naught of E. And this, it depends only, phi depends on F, can be fixed, and it's true for anything bigger than this phi. Phi is, I mean, the support of phi is of very special type, but there is a sequence that is true, and the IMRN formula is true for any large phi. And so you will have this. Now, look at the case of GL2. Now let H be equal to GL2. Then this omega naught of E is just the C of WL. And what we have now proved, the assertion is that these two things are equal. B phi of G and F is equal to B phi of G and F naught. Okay. Now in this case, omega naught of E is just going to be the big cell. So we will conclude that there exists an F naught, which is of compact support in C of WL, transforms according to omega pi. And then if not, with using this thing, because integration was a Mellin transform, let me write it, let me denote it by MF. It's a Mellin transform of this P sub phi of G and F. And this is over the big cell. I can replace it by Mellin transform of P sub phi of G and F naught. And now, if I take my representations, not twist them by highly ramified characters, I still have the equality. Then Mellin transform, I'm just going to write it like this, is going to be equal to Mellin transform integration is over the big cell. We have a function of compact support. You can get uniform smoothness, meaning that, I mean, you can find a smoothness on a small neighborhood, and then the standard tricks from the stability will show that if chi is highly ramified, this is going to be equal to 0. Just an example. Yeah. No, we need the whole thing. Just an example. And so it tells you that you have this thing is equal to 0. Now let's go back to our situation. This is now shows that H tensor chi is equal to Mellin transform of P sub phi of G H prime tensor chi, because F was just because F was just H minus H prime. So we have these two things equal. Now this side is equal to the inverse of those two gamma functions. Standard 2s pi H2, and then in fact inverses of this, and this is for pi and that's for pi prime. Pi prime standard, and gamma again inverse gamma of 2s pi prime H2 inverse, and twisted by chi. Twisted by chi, twisted by chi, twisted by chi, twisted by chi. So we have these things. We know these two are equal for highly ramified characters. These are, you can use Jacquet and Shalaika. We know these are equal, so we can conclude the other ones are equal. So the general strategy is just to, we have proved many lemmas, just to try to cut off, I mean, take off things. In the case of GL3, it seems that it's not going to be just this. There may be some other functions which only depend on the central character. You take these go away, you get rid of them, and then you break it up level by level. The main issue is that you will only have to work with these relevant Weyl group elements. These are Weyl group elements that if you multiply by WL, they become a long element in a Levy subgroup. And these are the ones which support Bessel functions. So basically, you just get rid of everything when when W doesn't support anything. You reach the next level when W does, you start cutting off something from them, and then move on. So that should eventually give us a proof. Yeah, for the Tsai, you again have the same thing, yeah, same problem. But the techniques we are using, this thing is pretty robust, the argument for reducing it to the, supercuspidal stability. And then, if we really get some nice things in this case, these germ expansions are quite general. You should be able to imitate it in general and prove it for all these cases. So this would be one, the main general goal would be to prove stability in general. That's what I wrote. The title of my IMRN paper was towards general stability, but I could be wrong. Thank you.